Now, I think the one which is applicable on our analysis today will be the magnetic nodal. That's the first from the second list. Once magnetic nodal is selected, I click on OK. That means everything else belonging to other engineering disciplines or analysis, they should be eliminated from the lists which we are going to have. So for example, when it comes to the choice of the element type, only element types in connection with electromagnetic type analysis will be visible, but the rest will be away from those lists. Okay, so I think it would be a good idea now to choose an element type. We do it from the preprocessor. Element type, add, edit, delete. You get a new window like this. This should not be strange to you because you've done it. You should have done it many times now. And then click on add. You get the second window. And I think the one which is relevant for our analysis today could be available from the magnetic vector, which is highlighted. And then the first one should be good enough for our analysis today. That is quad 4, node 13. Yes? So when it is highlighted, then I click on OK. And then I don't need to control its options. I will try to utilize the default for now. So I just need to close this window, but you can see that now plane 13. Plane 13 is the one which we have just selected for our analysis. So close this window. And again, my advice, guys, in order to maybe minimize the effect of any possible crash, my advice would be to save maybe the model from time to time. So by now, I think we've already provided a name for the job. So it's a matter of pressing that button, the save button. And that will automatically save the model under that name. So I'm going to save it now. We haven't done anything massive so far, but I think you need to do it regularly. Okay, so that's the element type. Second, I think we need to provide the material properties. So I go to material properties, and then material models. Then I get the usual window. Now, this is the first one, the first material property that I'm going to input, and that's why I get material model number 1 on the left-hand side of the window. On the right-hand side now, electromagnetics, this is the type of the analysis which I'm doing, so I need to click on that one. And then I need to provide the relative permeability of the material. So click on the relative permeability and then on constant, because this is the assumption which I'm going to provide for that property across the material. Now, I need to provide now the permeability, the relative permeability for 3 different materials. Remember, we have non-magnetic material, which is the coil, and then the fluid material, and then the magnetic materials for the piston and the cylinder. When it is non-magnetic, obviously the permeability should be 0 or above. ANSYS, for one reason or another, doesn't allow a 0 value for the permeability. So when it is a non-magnetic material, we need to provide a value of 1. Yeah? So we need maybe to input 1 here in the Murex box. Click on OK. So once you click on OK, you get now under material model number 1, you get permeability constant as something being defined. Now, this is material number 1. So we know in our approach that material number 1 will be what? Will be the non-magnetic material. Yeah, because later on we need to assign these properties to the right materials. Okay, so we repeat this. We go to material, click on, and then new model, and then obviously the second one should be reference 2, and then click on OK, and then repeat what you did with the first one. So you need to double click on, or just click on constant for relative permeability. Now this is material number 2, and I'm going to assume that material number 2 should be the fluid material, the smart fluid material, for which I am proposing a permeability of 50. So I need to input a value of 50. And then click on OK. You could see now material number 2 has already been defined with a constant permeability. We repeat this for the third time. So material, and then new model. Now the reference will become 3. So click on OK. And then go back to the relative permeability, which is still constant. Now the third material should be what? The magnetic material in my approach. And I think for this one, as it is mentioned, I think on the data sheet, I am proposing to use a low carbon material. Low carbon materials, they could come maybe with a relative permeability of around 1,000. I'm going to propose 950 for this one in particular. But if you examine the literature, you will see that some of the materials, they could go to 10,000 permeability, and some supermagnetic materials. I think there is one which is called the new metal, NU metal. This goes up to something like 100,000, and that's a super magnetic conductor, which is used in order to make very sophisticated devices, electromagnetic devices. But for now, I think we will use low carbon material with a permeability of 950. So I just need to input 950 here. And then click on OK. And that's basically the third material in our table, which we require. So we should close this window. And then I need, just now I need to save it. Yeah? So we have done now the element type, we've done the material properties. It might be a good idea to start with maybe the model itself. Yeah? So we do this from, again, the preprocessor on the main menu on the left-hand side of the window. So we just need to go down into the list. We click on modeling, on create, and we need to create areas. Again, if you remember, I think as part of my introduction to the software, we said you could start maybe from the lower end of the menu for the creation of these solid entities, and you start from key points, and then you connect them with lines and so on, until you go to the top. Or you start from the opposite end, from maybe some shapes which are available as part of answers. Now we are going to generate just rectangular areas, and these are shapes that are these are shapes available through maybe the main menu. So when you click on modeling, create areas, then you click on rectangular, and then by 2 corners. So usually we try to envisage the global origin, which has x, y, z equivalent to 0. We need to reference everything else accordingly to that global origin. Now, for today, I'm going to assume that the global origin should coincide with the lower left-hand end of the actuator. So remember, we have an area rectangular area like this for the actuator. The corner on the left lower end, yeah, that should be the global origin. So I could start maybe with the creation of the larger area, assuming that that corner will coincide with what? With the global origin. So 0 for x and 0 for y. Width is 9 centimeters. So 9. And the height is 4.9 centimeters. Click on apply. And then you should be able to get an area like this. Yeah? Now we need to create the fluid area. So the fluid area will start from x0 at height of 2 centimeters. Width is 9 again. And height is 0.2, so 2 millimeters, 0.2 centimeters. So again, in this box, we need to provide x is what? 0, y is 2, width is 9, and height is 0.2. So 0 again for x, 2 for y, width is 9, and height is 0.2. Click on apply. I should be able to see the fluid area with its boundaries. Yes? Now we need to create the coil areas, the two cross-sectional areas of the coil. So I start with the left-hand side. It's like a square here. So we know the dimension is 1 by 1 into the last 2 boxes, into this window. While the x and y for the lower end of that coil area, x should be 2. Is it 2? X is 2, yeah? So x is 2, while y is 2.4. So again, in this box, we should provide the x coordinate for the corner point of this new square area of the coil as 2 for x. For y should be 2.4. The width of the coil area is 1 centimeter, and the height is 1. So again, guys, 2, 2.4, 1, and 1. Yeah. Are you in good pace with me? Yeah? Okay. So click on apply. And now you should be able to see the first cross-sectional area of the coil, which is on the left-hand side. Now we need to create the one on the right-hand side. So it's like another box here. Now for the corner of that rectangular or square area, its coordinates should be 6 along x and 2.4 along y, while the width and height should be 1 by 1 centimeter. So this is the thing which we are going to supply in this case. X should be 6, y should be 2.4, width is 9, while height is, width is 1, and height is 1 as well. So again, 6 and 2.4, these are the coordinates of the corner of this new square. The dimension of the square should be 1 by 1 centimeters. And now this is the last one we need to create. So instead of maybe clicking on apply, you need to press OK. And then you should be able to get what the second cross-sectional area of the coil. And then I think at this time it would be a good idea to what? To save it. Yeah. Thank you. So, if I list areas you'll see that according to the table here, we have what? We have 4 areas. Each of them has one loop to define the boundaries. And the boundaries of these areas are defined by these lines. Each of the lines, of course, should have its own reference. Now, you could go to plot controls, numbering, and decide to show the number of these areas on your figure. So you could see that area A1, this should be the larger area. Now, it may not be visible, but I think if you attended the class on Friday and you followed my instructions with regard to the utilization of the logic select commands, then you should be able to execute them, and eventually you should be able to find out, I think, which is which. But for now, this is something simple. You could put, for example, the numbers on the lines, and you'll see that now area 1 is defined by lines or loop with lines 1, 2, 3, 4. So you could see that line 1 should be here, that's 2. That's number 3, as you could see, and that's number 4. And so on for the rest. You could check now each one, each area according to its lines as it appear, or as they appear in the table. Yeah? So how many areas we have so far? We have 4. Okay, so if we close this window, now we need to overlap them. So I go to the operate command, again from modeling operate, and then I could click on booleans, and then on overlap. I need to overlap areas, so I click on areas, and I should get a window here, like this one, inviting me to select the areas. So again, guys, I'll go through this again. I need to overlap the areas. I access them from the booleans. I should reach that one from modeling, operate, booleans, overlap, and I need to overlap areas. So once you click on areas, you end with the window on the right hand side. Basically, I need to select the areas that I need to overlap one by one. In fact, I need to overlap all of them. So there is an option at the bottom end of this window where you could see pick all. I'm going to press on pick all, and then you'll see the areas, all the areas should have been overlapped now. Now, if I go back to list on list areas, now this is different to what we saw before. So you can see now we have 5 areas instead of 4, starting from 2 and ending with 6. Now for areas 2 to 5, each of them is defined by what? Is defined by a single loop. So for example, area number 2, and this is defined by lines 5, 6, 7, and 8. So this should be what? This should be the purple area, which is the fluid area. Lines 5 here, 6 there, 7 there, and 8 there. And so on for area number 3, area number 4, area number 5. But number 6, you will see that it has 3 loops. And this is definitely the piston area. So the boundary, which is the first loop, should be defined by lines 19, 3, 20, and 7. So this is 19, 3, 20, and 7. And the other two loops, they should define the inner areas, the holes. So the first one, area 6, loop 2 should be defined by lines 10, 9, 12, 11. So these are 10, 9, 12, 11. And likewise, the third loop should define the recess of the actuator secondary cross-sectional area. So by that time, we have what? We have created these areas. They are individual areas, but they are attached to each other, so they are not floating in the space. After we've done this, I think we should close this window to show the list of these areas. And I think it would be a good idea now to remove their numbers. We don't need their numbers from now. So I go to port control, numbering, and deselect the areas and lines. And I think again, we need to save the model, which we have done so far. Yeah. So this is the physical model which I need to utilize maybe further into my analysis. Now what I need to do next, I have defined the electron, I have defined the material properties, I have created the model. Basically now, if I need to proceed with the solution, I need to mesh the model. So this is where I create the elements and the nodes. I remember the finite element equations, they are solved where? The nodes. So without the meshing, I won't be able to solve the model. Now, for this one, you will see that the meshing process will be subdivided into 3 different steps. And the first one, we did it maybe indirectly in the first 2 exercises when we needed to observe the particulars attached to, if you like, the attributes. Yeah, that's what I mean. The attributes of the maybe the area that we need to mesh. But I think it will be more important in this exercise that step. Why? Because we have 3 different materials, so we need to attach them. We need to associate them with their relevant areas. So when we mesh the model is meshed with the right properties for each of the materials. So that's the first step. And the second one, we need obviously to provide the size of the element. So we could decide on the mesh density. And in the third step, we need to execute the meshing. Yeah? So we start with the first step. We go to meshing, start working from the preprocessor, so meshing. The first option is mesh attributes, and then we need to do them on areas, so picked areas. And once you click on picked areas, you get a window like this, inviting you to select the area. So now in our decision, in our approach, we have 3 materials with the 3 different properties, particularly their permeabilities. So material number 1 is what? Is non-magnetic material, which is the coil. The second material was what? The fluid material with its permeability number 2, under number 2. And the third one, obviously, the cylinder and the piston with their material properties, permeability of 950. So now, I need to start with the first one. I need to select the 2 coil areas. So click on the first one, should be highlighted, and then click on the second one. You could see now the 2 areas of the coil, the single coil, they are highlighted. Then click on apply in the box, and then you get a new window showing the particulars, the attributes of that area. So by default, material number 1 is attached to them, which is what we need. So again, under our approach, material number 1 should have a permeability of 1 or 0. Yeah, by default. And then we have only one element type, When the problem becomes more sophisticated, then highly likely that the solution cannot be achieved with a single element type. So you need to provide more than one. And then when it comes to the meshing and the association of these elements to the right areas, obviously this is the place where you need to do it. But we have only one plane type, so it's plane 13. This is going to be maintained. Everything should be fine. I should click on apply. And then this window is still open, so I just need to select the second area. Now the second area should be the fluid area. So I click on the fluid area, and you could see that it is being highlighted now. And so click on apply again in the box. And by default, material number 1 is still on, so that's wrong for the fluid area. We have already decided that the capability under material number 2 is 50, which is applicable on the fluid area. So we change it from reference 1 to reference 2, like you could see here. The rest of the information will be okay, and click on apply. We haven't finished. Now we need to select what? The cylinder and the piston areas. So you select maybe the cylinder here and the piston. You can see they are highlighted. And then you click on apply again in the box. And you get the usual window. Now we need to change reference 2 to what? 3. Thank you. And under 3, the probability is 950. So basically, we tell the software that the cylinder and the piston, they are made from a magnetic material for which the probability is 950. Okay? So this is the last one. So we don't need to click on apply, we need to click on OK. Yeah? If you've done this, I think we just need to save the model again.